What is an exponential function?
Along with exponents come exponential functions, or the relationship between values of a variable and the numbers formed by raising some positive number to the power of those values. In functional notation, an exponential function is written f x equals x, in which a is a positive number. For example, the function f x equals 2x is an exponential function. In logarithmic terms, an exponential function is most commonly written as exp or x, in which e is called the base of the natural logarithm. These types of functions are usually shown on a graph. For more information about graphs, see geometry and trigonometry. As a function of the real variable x, the resulting graph of x is always positive, or above the x-axis and increasing from left to right. Although the line of such a function never touches the x-axis, it gets very close to it.
What are vertical asymptotes in association with limits?
Using the example above, as x gets closer to 3, the points on the graph get closer to the vertical line x equals 3. Seen as a dashed line on the graph on p. 218, this line is called a vertical asymptote. The above chart shows 4 of the vertical asymptotes for the given function f, x, and their notations.
When was a mechanical calculating device first used for the American census?
When government officials estimated that the 1,890 census would have to handle the data from more than 62 million Americans, there was a slight panic. After all, the existing system was slow and expensive. Using tally marks in small squares on rolls of paper, which were then added together by hand. One estimate determined that such an endeavor would take about a decade to complete, which would be just in time to start the process all over again for the 1900 census. In desperation, a competition was set up to invent a device that could easily count the 1,890 US census. Thus, in the 1880s, American inventor Herman Hall Erith, 1860 to 1929, who is also known as the father of modern automatic computation, presented his competition-winning idea. He used Jacquard's punched cards to represent the population data. Then read and collated the information with an automatic machine. With his automatic tabulating machine and automatic electrical tabulating device, Hollerith would put each individual's data on a card. With a large number of clock-like counters, he would then accumulate the results. From there, he would use switches so the operators could instruct the machine to examine each card based on a certain characteristic, such as marital status, number of children, profession, and so on. It became the first such machine to read, process, and store information. The machine's usefulness did not end there, though. Eventually, Hollerith's device became useful for a wide variety of statistical applications. Certain techniques used in the automatic tabulating machine were also significant, helping in the eventual development of the digital computer. Hollerith's company would also eventually become well known, becoming International Business Machines, or IBM, in 1924.
What is a point spread?
A point spread is the predicted scoring difference between a game's two opponents. It is used by bookmakers to equalize two teams for betting purposes. For example, if a person chooses the team that is favored, the gambler has to win by more than the point spread in order to get credit for a correct pick. If the underdog team is chosen, the bettor must lose by less than the spread number in order to get credit for a correct pick. If a point spread is listed as off, this means there is no official point spread for the game. For example, if a person picks Army to win, and the team is favored to beat Navy by 5 points, called a spread of 5 points, Army must win the game by 6 or more points in order for the bettor to win. If Army wins by exactly 5 points, the game is called a push, and no one wins.
What was the Roman calendar?
The first Roman calendar, according to legend, appeared when Rome was founded around 750 BCE. When it actually started is still up for discussion. But the calendar was based on the complexity of the solar-lunar cycles. At first, the calendar had 10 months, starting in March. January and February were added as the calendar was modified. Politics entered into the determination of this calendar, too, with certain officials deciding to add days whenever they desired, and even what to name certain months.
Why were counting devices developed?
Early counting devices were developed for a logical reason: to allow people to count items in order to trade or to keep track of stock, such as cattle. They also used simple counting devices to keep track of the seasons, mostly for agriculture, in other words, to know when to plant, and for religious reasons, such as marking days for certain feasts. For more about counting in ancient times, see History of Mathematics.
Who was considered the first statistician?
English statistician and tradesman John Grunt, 1620 to 1674, was the first true statistician and wrote the first book on statistics. Although statistics in a simpler form was known long before that. Grunt, a draper by profession, was the first to use a compilation of data, which in this case involved the records of bills of mortality, or the records of how and when people died in London from 1604 to 1661 in his natural and political observations made upon the bills of mortality. He determined certain inclinations, such as more boys were born than girls, women tend to live longer than men, etc. He also developed the first mortality table, which showed how long a person might expect to live after a certain age. A concept very familiar to us today, especially in fields such as insurance and health.
Who was Francois Veit?
French mathematician François Veit, or Franciscus Vitat, 1540 to 1603, is often called the founder of modern algebra. He introduced the use of letters as algebraic symbols, although Descartes see below introduced the convention of letters at the end of the alphabet X, Y, for unknowns and letters at the beginning of the alphabet A, B, for knowns, and connected algebra with geometry and trigonometry. He also included trigonometric tables in his Canon Mathematicus. 1571, along with the theory behind their construction. This book was originally meant to be a mathematical introduction to his unpublished astronomical treatise, Ad Harmonicon Coelest. For more about Veit, see Algebra and Geometry and Trigonometry.
How are graphs used to solve equations?
Any figure represented by an equation in two variables is a curve in two dimensions. For example, the equation 3x plus 4y equals 8 is also called a linear because the solution represents a line, which is considered a curve in function geometry, on a graph. There are also graphs of equations in three variables, with the solution as a surface or the two-dimensional outer layer of a three-dimensional object.
What are first-order homogeneous and non-homogeneous linear differential equations?
These differential equations may be long-winded phrases, but they are actually types of first-order differential equations. A first-order homogeneous linear differential equation can be written in the notation as follows: Ty, t, plus a, t, y, t, equals 0. The first-order homogeneous linear differential equations are those that place all terms that include the unknown equation and its derivative on the left-hand side of the equation. On the right-hand side, it is set equal to 0 for all t. The non-homogeneous linear differential equations are those that, after isolating the linear terms containing y, t, and the partial differentials inside the above large parentheses on the left side of the equation, do not set the right-hand side identically to 0. It is often represented by one function, such as the b, t, see below. The standard notation is as follows: ty, t, plus a, t, y, t, equals b, t, usually in reference to time. Such problems are called initial value problems. The other condition is the boundary condition, in which constraints are specified this time at the boundary points, usually in reference to space, with such problems called boundary value problems.
What is physics?
Physics is often described as the science of the interactions between matter and energy. It includes the subfields of atomic structure, heat, electricity, magnetism, optics, and many other phenomena. Traditionally speaking, physics is divided into classical and modern, although many subdivisions of the two overlap and both are ruled by mathematics. Classical physics includes Newtonian mechanics, thermodynamics, acoustics, optics, electricity, and magnetism. Modern physics includes such fields as quantum field theory and relativistic mechanics. Other common divisions of physics are experimental and theoretical physics. Theoretical physicists use mathematics to describe the physical world and predict how it will behave. They depend on experimental results to check, understand, change, or eliminate theories. Experimental physicists test their predictions with practical experiments, often using mathematics to conduct the experiments.
What is the composition of the air?
Meteorologists determine the composition of air by analyzing its various constituents. These are mainly displayed in terms of percent of the atmosphere. The first 40 to 50 miles, 64 to 80 kilometers above the surface contains 99% of the total mass of the Earth's atmosphere. It is generally uniform in composition, except for a high concentration of ozone, known as the ozone layer, at 12 to 30 miles, 19 to 50 kilometers, in altitude. In the lowest part of the atmosphere, the area in which humans, other animals, and plants live, the most common gases are nitrogen, 78.09%, oxygen, 20.95%, argon, 0.93%, carbon dioxide, 0.03%, and minute traces of such gases as neon, helium, methane, krypton, hydrogen, xenon, and ozone. Water vapor is also present in the lower atmosphere, although variable and at a very low percent. Higher in the atmosphere, the composition and percentages change as the atmosphere thins. For more about percents, see Math Basics.
What is an indefinite integral?
From the above, we learned that when the limits of integration in the case of a and b above are specified, it is called a definite integral. Contrarily, if no limits are specified, it is called an indefinite integral. Thus, the indefinite integral is most often defined as a function that describes an area under the function's curve from some undefined point to another arbitrary point. This lack of a specified first point leads to an arbitrary constant, usually denoted as c, that is always part of the indefinite integral.
How is mathematics used to determine resistor values in an electrical network?
Electrical engineers who deal with systems and circuit theory need to know the terms and functions of the basic circuit element resistor, capacitor, and inductor in terms of current voltage associations determined by impedance, obstruction, complex numbers, calculus, and Laplace transforms, see above, are all mathematical concepts used to understand circuit theory. The best way to understand the basics are through the following simple equations. Resistor voltage equals current, I, times resistance, R, or V equals IR. Capacitor voltage equals the square root of -1, J, often called I, or an imaginary number, times frequency. W, times the capacitance, C, all times the current, I, or V equals, JWC, I. Inductor voltage equals the current divided by the square root of -1, J, times frequency, W, times inductance, L, or V equals I/JWL.
Why were early Greek calendars such a mess?
And like the Mesopotamian cultures, the early Greeks paid less attention to astronomy and more to cosmology. They were interested in studying where the Earth and other cosmic bodies stand in relation to the universe. Because of this, their astronomical observations were not accurate, creating confusing calendars. This also led to a major conundrum: almost every Greek city kept time differently. In fact, during the Greek and Hellenistic times, most dates were given in terms of the Olympiads. This only created another timekeeping problem: if something happened during the 10th Olympiad, it meant the event occurred within a 4-year span. Such notation creates headaches for historians, who end up making educated guesses as to the actual dates of Greek events. Important people's deaths and births, and other significant historical occurrences.
What do computers and arithmetic have in common?
Computers and arithmetic have a great deal in common. Arithmetical operations are actually digital computer operations in which the numerical quantities are computed either through adding, subtracting, multiplying, dividing, or otherwise comparing them. Arithmetical instructions give a computer program direction to perform an arithmetic operation on specific types of data, such as addition, subtraction, multiplication, and division. The sections of the computer that carry out these computations and other logic operations are called arithmetical units, or arithmetic sections. For more information about computers and math, see Math in Computing.
What Greek mathematician made major contributions to geometry?
The Greek mathematician Euclid, c. 325 c. 270 BCE, contributed to the development of arithmetic and the geometric theory of quadratic equations. Although little is known about his life except that he taught in Alexandria, Egypt, his contributions to geometry are well understood. The elementary geometry many of us learn in high school is still largely based on Euclid. His 13 books of geometry and other mathematics, titled Elements, or Stoicheion in Greek, were classics of his day. The first 6 volumes offer explanations of elementary plane geometry, the other books present the theory of numbers, certain problems in arithmetic, on a geometric basis, and solid geometry. He also defines basic terms such as point and line, certain related axioms and postulates, and a number of statements logically deduced from definitions, axioms, and postulates. For more information on axioms and postulates, see Foundations of Mathematics. For more information about Euclid, see Geometry and Trigonometry.
What are some common modern measurement systems?
There are several measurement systems in use today. The English customary system is also known as the standard system. U.S. customary system, or units, or English units. It actually consists of 2 related systems, the U.S. customary units and the British imperial system. The background of the units of measurement is historically rich and includes modern familiar terms, such as foot, inch, mile, and pound, as well as less well-known units, such as span, cubit, and rod. The official policy of the United States government is to designate the metric system as the preferred system for trade and commerce. But customary units are still widely used on consumer products and in industrial manufacturing. In order to link all systems of weights and measures, both metric and non-metric, there is a network of international agreements supporting what is known as the International System of Units. It is abbreviated as SI, but not SI. In reference to the first 2 initials of its French name, Système International des Unités. It was developed from an agreement signed in Paris on May 20, 1875, known as the Treaty of the Meter, Convention du Meter. To date, 48 nations have signed the treaty. The SI is maintained by a small agency in Paris, the International Bureau of Weights and Measures. BIPM, or Bureau International de Poids et Mesures. Because there is a need to change or update the precision of measurements over time. The SI is updated every few years by the International General Conference on Weights and Measures, or CGPM, or Conference Générale de Poids et Mesures, the two most recent meetings being in 2003 and 2007. SI is also referred to as the metric system, which is based on the meter. The word can also be used in mathematics, for example, metric space, or even computing, font metric file. It is often referred to incorrectly as metrical. See below for more about the metric system.
What is mathematical medicine?
Mathematical medicine uses math to understand certain medical problems. For example, some medical researchers are using noises and sounds from a patient's lungs as a diagnostic tool. Based on the quality of the sound measured by ear or mathematical analysis of a frequency spectrum, it may prove to be a non-invasive way of detecting lung disease. Other examples are the mathematical modeling of how drugs are delivered through the body to target diseases and the mathematical modeling of the progression of age-related macular degeneration. Overall, mathematical modeling and simulation techniques are the most important part of mathematical medicine, and will likely be used in the future to help solve problems with the human body.
What is an Argand diagram?
An Argand diagram is a graphical way of representing a function of a complex variable, often written as z equals x plus e, in which x, y, and z are coordinates in three-dimensional space and I is an imaginary number. Its true discoverer is not actually known, but Swiss mathematician Jean-Robert Argand, 1768 to 1822, is given credit for the diagram. It is thought that this was also independently discovered by Danish mathematician Caspar Wessel, 1745 to 1818, and later by German mathematician and physicist Carl Friedrich Gauss, 1777 to 1855, in 1832, but he probably determined it much earlier, thus, its other name is the Gaussian plane.
Why did the need for mathematics arise?
He reasons humans developed mathematics are the same reasons we use math in our own modern lives. People needed to count items, keep track of the seasons, and understand when to plant. Math may even have developed for religious reasons, such as in recording or predicting natural or celestial phenomena. For example, in ancient Egypt, flooding of the Nile River would wash away all landmarks and markers. In order to keep track of people's lands after the floods, a way to measure the earth had to be invented. The Greeks took many of the Egyptian measurement ideas even further, creating mathematical methods such as algebra and trigonometry.
What is the order of operations when one simplifies an algebraic equation?
Here is a certain order to working out an algebraic equation. The following lists the operations in their correct order. Do what is inside the parentheses. Do the exponents. Do all the multiplications and divisions from left to right. Do all the additions and subtractions from left to right. There are also rules when it comes to grouping in algebraic equations, especially when working with parentheses. When an expression has parentheses within parentheses, work from the inside out, removing the innermost parentheses first. And remember, if there is a positive sign in front of the parentheses, it does not change any sign inside the parentheses. If there is a negative sign in front of the parentheses, it will change all the signs within the parentheses.
How can people calculate their age and weight on other planets?
It is certainly possible to find a person's age and weight on another planet without actually having to travel there. To figure out weight, one just needs to know the gravitational pull on another planet, moon, or other space body. For example, based on the chart below, if a person weighed 100 pounds on Earth, he or she would weigh 38 pounds on Mercury, 100 x 0.38. A person's age on Earth depends on how many times the planet has orbited the Sun during his or her lifetime. For example, a person 30 years old has traveled around our star 30 times. In order to work out how old a person is on another planet, the person's age has to be divided by the period of revolution, in terms of Earth years. Thus, if the same 30 Earth-year-old person lived on Saturn, he or she would be just over 1 Saturn-year-old, 30/29.5 equals 1.02 Saturn years. On Mercury, the person would be 124.5 Mercury years old, 30/0.241 equals 124.5 Mercury years.
How is unit price used to determine total price?
The unit price is simply the cost for each item, or unit. The term is often used to compare the cost of the same quantity of items that come in different sizes. Or it is used to determine total costs for services. For example, if a person was having a birthday party at a local restaurant for 100 guests, and each meal unit costs $7.50, the total cost of the celebration would be $7.50 x 100 equals $750. Add a tip to the total. See above, and it's easy to see why most people celebrate at home or only invite a few friends.
How many bases are in a human's genome sequence?
Here's a good reason why computers are so important to biologists working on the human genome. The amount of data is staggering, and would take scientists generations to analyze without the benefit of computers. For example, it would take about 9.5 years to read out loud. Without stopping, the 3 billion bases in a person's genome sequence. This is calculated on a reading rate of 10 bases per second, equaling 600 bases per minute. 36,000 bases per hour, 864,000 bases per day, and 315,360,000 bases per year. 1 million bases, called a megabase and abbreviated MB, of DNA sequence data is roughly equivalent to 1 megabyte of computer data storage space. Because the human genome is 3 billion base pairs long, 3 gigabytes of computer data storage space are needed to store the entire genome. This includes something called nucleotide sequence data only and does not include other information that can be associated with sequence data. Because of such numbers, scientists working on the human genome are grateful they have computers on their side.
What was the House of Wisdom?
Around 786, the fifth caliph of the Abbasid dynasty began with Caliph Harun al-Rashid, a leader who encouraged learning, including the translation of many major Greek treatises into Arabic, such as Euclid's Elements. Al-Ma'mun, 786 to 833, the next caliph, was even more interested in scholarship, creating the House of Wisdom in Baghdad, one of several scientific centers in the Islamic Empire. Here, too, Greek works such as Galen's medical writings and Ptolemy's astronomical treatises were translated. Not by language experts ignorant of mathematics, but by scientists and mathematicians such as Al-Kindi, 801 to 873. Muhammad ibn Musa al-Khwarizmi, see below, and the famous translator Hunan ibn Ishaq, 809 to 873.
What are ratios and proportions?
A ratio is the comparison of two numbers. It is most often written as a fraction or with a, as in 3/4 or 3:4 to separate the two numbers. For example, if we want to know the ratio of dogs in a shelter that houses 24 animals to the total count, we first determine the number of dogs, say, 10, then the ratio of dogs to animals in the shelter becomes 10/24, or 10/24. Which is also said as 10 to 24. But there are rules to ratios. For example, Order matters when talking about ratios, therefore, the ratio 7:1 is not the same as 1:7. A proportion is an equation with a ratio on each side, and is a statement that two ratios are equal. For example, 1/2 equals 4/8, or 1/2 is proportional to 4/8. In order to solve the proportion, or when one of the four numbers in a proportion is unknown, we need to use cross products to find the unknown number. For example, to solve for x in the following, 1/4 equals x/8, using cross product, 4x equals 1x8, thus, x equals 2.
What are some terms used in the Cartesian coordinate system and graphs?
There are numerous terms used in the Cartesian coordinate system. Besides the ones already mentioned, the following are some of the most common. An intercept is a point's distance on a coordinate system axis from the origin to where a curve or surface intersects the axis. On a graph, the x-intercept and y-intercept are two important features that show where a line cuts through the x and y axes, respectively. The origin is the fixed point from which measurements are taken. In most cases, especially in a standard simple two-dimensional Cartesian coordinate system, this means the point that represents 0. This is often seen as 0, 0, or the point in which the x and y axes intersect on a graph. In a three-dimensional system, the coordinates are often seen as 0, 0, 0. A Cartesian plane, or coordinate plane, is described as a two-dimensional space made up of points that are identified by their relation to the origin, 0, and the x and y axes. An axis, the plural is axes, is a reference line used in a graph or a coordinate system, such as the Cartesian system. For example, the x-axis and y-axis are perpendicular lines on a graph in a two-dimensional system. In a three-dimensional system, they are the x-axis, y-axis, and z-axis. Collinear points are those that lie on a straight line. Any 2 points are considered collinear because a straight line passes through both. Many procedures in analytic geometry involve determining the collinear points that represent coordinates that solve an equation. Logically, those points that do not lie on the same line, or, in other words, that do not solve the equation, are called non-collinear points.
What are some examples of clock arithmetic?
As stated above, the clock would be considered arithmetic modulo, with calculations including such statements as shown below. Note, in all of the first calculations, the equal sign can be replaced with the congruence sign 3 lines instead of the 2 for an equal sign.
What are differential and ordinary differential equations?
Logically, a differential equation is one that contains differentials of a function, with these equations defining the relationship between a function and one or more derivatives of that function. More specifically, differential equations involve dependent variables and their derivatives with respect to the independent variables. To solve such equations means to find a continuous function of the independent variable that, along with its derivatives, satisfies the equation. An ordinary differential equation is one that involves only one independent variable.
What is the definite integral?
In actuality, the area is actually determined using limits. In the function f, x, as n gets larger, the numbers determined by left n, and right n, will get closer and closer to the area n.
Who was M. C. Escher?
Moritz Cornelius Escher, 1898 to 1972. Was a Dutch painter famous for his mixing of art and mathematical concepts. He had no formal math training past secondary school, but he was, and still is, admired by mathematicians for his amazing visualizations of mathematical principles. Escher's interest in mathematical patterns began around 1936, after viewing the Alhambra Palace's collection of Islamic art, see above. He was fascinated with structures represented in plane and projective geometry, both Euclidean and non-Euclidean geometry. For more information, see geometry and trigonometry. Not only using the geometry of space, but also the logic of space. For example, he used the idea of tessellations, or arrangements of closed shapes, usually polygons or similar regular shapes, like those used on a tiled walkway, that cover the entire plane without overlaps or gaps. Not only did he use regular tessellation shapes, but also irregular ones, making the shapes change and interact with each other. He also made many of his amazing patterns by taking a basic pattern and either distorting it or applying what geometers call reflections, translations, and rotations. For many other mathematical patterns, he used regular solids, Platonic solids, and visual aspects of topology in his work. For more about Platonic solids, see geometry and trigonometry.
Have computers been used to determine the value of pi?
Yes, computers have been used to determine the value of pi. But no computer has yet found the final number in the long progression of numbers. They probably never will, because pi is considered to be an infinite number. But for the sake of just trying, larger and faster computers are often used for this task. To date, pi has been found to more than 6 billion places. For more about pi, see mathematics throughout history.
What is sea level?
Sea level is the height of the ocean's surface at a certain spot and depends on changing conditions. It is also the basis for most Earth surface measurements. Because sea levels are used as a reference point in determining land elevations and ocean depths, scientists have averaged out the highest and lowest altitudes and depths from sea level locations. The highest is Mount Everest, Nepal, Tibet, which measures 29,022 feet, 7 inches, 8,846 meters, above sea level. The lowest on land is the Dead Sea, Israel, Jordan, which measures 1,299 feet, 396 meters, below sea level. The greatest depth below sea level is the Mariana Trench in the Pacific Ocean. A deep chasm measuring 36,201 feet, 11,033 meters, below sea level.
What was the Sumerian oral counting system?
The Sumerians, whose origins are debated, but who eventually settled in Mesopotamia, used base 60 in their oral counting method.
What other variables are often used in statistics?
When an experiment is conducted, variables manipulated by the experimenter are called independent variables. Also independent factors. While others measured from the subjects are called dependent variables, also dependent measures. For example, consider a hypothetical experiment on the effect of lack of sleep on reaction time. Subjects either stayed awake, slept for 2 hours for every 24, 5 hours. For every 24, or 8 hours for every 24, they then had their reaction times tested. The independent variables would be the hours slept by each person, and the dependent variables would be the reaction time. Some variables can be measured on a continuous scale, a continuous variable being one that, within the limits the variable ranges, can take on any value possible. For example, we can make the time to eat a lunch at a certain restaurant be the continuous variable because it can take any number of minutes or hours to finish the meal. But other variables can only take on a limited number of values or dependent variables. For example, if the variables were a test score from 1 to 10, then only those 10 possible values would be allowed. These are called discrete variables.
What are subjects and predicates in Aristotelian logic?
In Aristotelian logic there are grammatical distinctions between a subject and a predicate. The subject is usually an individual entity, an object, house, city, man. Animal, or it may be a class of entities, objects, houses, cities, men, animals. The predicate is the property or mode of existence that does or does not exist with a given subject. For example, a singular plant, subject, may or may not be blooming. Predicate, all houses, subject, may or may not have 2 stories, predicate.
Are there double and triple integrals?
Yes, there are double and triple integrals and even multiple integrals in equations, jj, and so on. For example, the integration of a function of 3 variables, w equals f, x, y, z, over a 3-dimensional region R in xyz space, 3-dimensional space, is called a triple integral.
What is the concept of relative frequency?
Relative frequency is actually another term for proportion. It can be found by dividing the number of times an event occurs by the total number of times the experiment is done. In probability, this is often written in the notation RFN, E, equals R/n, in which E is the event. N is the number of times the experiment is repeated, and R is the number of times E occurs. For example, a symmetrical coin can be tossed 50 times, N. In order to find out how many times tails will occur, E. If the result is 20 tails, R, and 30 heads, then the equation becomes 20 fiftieths, or 2 fifths equals 0.4, or the relative frequency is 0.4 for tails. If this experiment is repeated over and over, the relative frequency will eventually get closer and closer to 0.5. Which is the true value that should result when tossing a 2-sided symmetrical coin.
How does one calculate resting heart rate?
Calculating resting heart rate, RHR, involves easy math. It is the number of heartbeats per minute when the body is resting, with the beats per minute representing the number of times the heart contracts. To measure the RHR, just count the number of beats per minute via the pulse usually taken either on the inside of the wrist or along either side of the neck for 15 seconds. Then multiply this number by 4, 15 x 4 equals 60 seconds, to get the heart rate per minute. Or count for 10 seconds, then multiply this number times 6. 6 x 10 equals 60 seconds, to get the heart rate per minute. For example, if you count 12 beats in 10 seconds, multiply 12 by 6 to get a resting heart rate of 72.
What are the least common multiple and denominator?
The smallest common multiple, whole number, of two or more whole numbers is called the lowest, or least, common multiple, LCM. For example, for the numbers 3 and 8, the multiples of 8 are 8, 16, 24, 32, and so on. The multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, 27, and so on. Therefore, the LCM of 3 and 8 is 24. The least common denominator, LCD, is mainly used to carry out the addition or subtraction of fractions. In order to do these operations, the fractions need to have the same denominator. For more information about fractions, see below. The easiest way to work on such calculations is to determine the lowest number possible for the denominator, a number called the least common denominator, LCD, which is actually the common factor by which two numbers are divisible. For example, to add 1/6 and 1/8, we have to find the least common multiple of the denominators. In this case, the number is 24, multiply 1/6 x 4/4 and 1/8 x 3/3, to change each addend to some number of 24 ths. Or 1/6 x 4/4 equals 4/24, and 1/8 x 3/3 equals 3/24. Thus, 1/6 plus 1/8 equals 4/24 plus 3/24 equals 4 plus 3/24 equals 7/24.
Are there higher derivatives of a function?
Yes, there are higher derivatives of a function, often referred to as higher order derivatives. The initial derivative is often written as f, x, but the is assumed in most cases. The next derivative is the second derivative, second order derivative, most often written as f, x. The next is the third derivative, or third order derivative, most often written as f, x. Fourth derivative, or fourth order derivative, most often written as f, 4, x, and so on.
What is an undefined term?
In terms of axiomatic systems, undefined terms are also called primitives. Although it sounds like doublespeak, these primitives are object names. But the objects they name are left undefined. The axioms are statements within the system that make assertions about the primitives. If a meaning is attached to a primitive, it is called an interpretation. Undefined terms are also found in a mix of axiomatic systems and geometry in which definitions are formed using known words or terms to describe a new word. There are three words in geometry that are not formally defined: point, line, and plane, because they can't be described without using words that are themselves undefined. These terms are fundamentally important in the study of geometry. because they are needed to further describe even more complex objects such as circles and triangles. For more about geometry, see geometry and trigonometry.
Why is finite element analysis important to many industries?
Finite element analysis, FEA, is important to various industries, especially those that need to predict failure of a structure, object, or material when under unknown stresses, because it allows designers to understand all of the theoretical stresses within the structure. This cuts manufacturing costs that would occur if a sample of the structure was actually built and tested. FEA uses a complex system of points, nodes, making up a grid called a mesh. The mesh is programmed to contain all the material, properties, and other factors that constitute the structure and determine how it will react to certain load conditions, such as thermal, gravitational, pressure, or point loads. The nodes are then assigned a density throughout the material, all depending on the stress levels anticipated in a certain area. In general, points with more stress, such as corners of a building or contact points on a car frame, will usually have a higher node density than those with little or no stress. As researchers examine the results of the FEA, they learn how the structure responds to the various stresses. In this way, a prototype of the structure won't have to be built until the majority of the theoretical kinks are worked out of the system.
What is a linear combination?
Linear combination is a combination or the sum of two or more entities, with each multiplied by some number, with not all the numbers being zero. Linear combinations of vectors, equations, and functions are common. For example, if x and y are vectors and a and b are numbers, then x and y is a linear combination. For more information about equations and functions, see Math Basics and Algebra.
What is Euclidean space?
Euclidean, also seen as Euclidean, space is often called Cartesian space, or more simply, n-space. It is made up of n dimensions and is a set of points, with each point represented by a coordinate of n components. Space with 2 to 3 dimensions and that does not use Einstein's and others' ideas of relativistic physics are considered Euclidean space. In Euclidean space, distance is defined by certain rules. The distance between 2 points is positive, unless they are the same points, the distance from points A to B.
How is the term surface used in mathematics?
When most of us think of the word surface, we often envision our own world, the thin outer crust of soil and rock we walk and live on. In engineering, the term means the outer part, or the skin with a thickness of 0, of a body. In science, it can apply to a plethora of objects, from geologic structures to micrometer-sized particles. In mathematics, surface also has numerous meanings. The most common denotes a two-dimensional topological space or three-dimensional Euclidean space. A surface in mathematics can be complicated and complex, such as in certain fractals, or extremely simple, such as in a plane.
What is a population pyramid?
A population pyramid is actually two back-to-back bar graphs that show the distribution of a population by gender. One shows the number of males and the other shows the number of females, most often in 5-year age groupings. These pyramids take a variety of shapes. For example, a triangular population distribution, also called a pyramid or exponential distribution, is usually indicative of a high birth and death rate, and a short life expectancy that is typical of less economically developed countries. A rectangular population distribution pyramid shows little change in size between the age groups. With more people reaching old age, this is typical of a more economically developed country. There are several uses for population pyramids. Besides calculating life expectancies, they are often used to find the number of dependents being supported in a specific population. Dependents in this case are considered to be children under 15, those attending school full-time and unable to work, and those over 65 years old or retired. Although this is a general definition and not applicable in all cases in all countries. Thus, governments can use such graphs to determine how much of the working population can support dependents. The graphs are also used to help predict future changes in terms of decades of a population's age structure. Historians use them, too, to find significant information based on past population pyramids.
How is geometry used to create Islamic patterns?
Many of the intricate patterns on Islamic architecture, structures, walkways, and fabric incorporate geometry in the construction of the design. From simple shapes, Islamic designs evolved into complex geometric shapes involving a high degree of mathematical symmetry. One of the best places to see such work is in the Alhambra Palace, a Moorish structure in Granada, Spain, built in the 15th century. Some Islamic designs were drawn by eye to be aesthetically pleasing. Others involved collaborations between mathematicians and artists. For example, mathematician and astronomer Abu al-Wafa, 940 to 998 CE. Born in today's Iran, worked with artisans in the 10th century, helping to design the ornamental patterns in wood, tile, fabric, and other materials. He discussed such mathematical concepts as constructing a perpendicular at the endpoint of a line segment, constructing a regular polygon, dividing segments into equal parts, and even the bisection of angles. Abu al-Wafa's teachings, and those of others like him, eventually led artisans to design the many intricate patterns seen in Islamic art today.
What is spherical geometry?
Spherical geometry is the study of objects on the surface of a sphere. This differs from the type of geometry studied in plane or solid geometry. In spherical geometry, there are no parallel lines, and straight lines are actually great circles, so any two lines meet in 2 points. In addition, the angle between two lines is the angle between the planes of the corresponding great circles. There are also entities called spherical triangles, or Euler triangles. When three planes pass through the surface of a sphere and through the sphere's center of volume, they have 3 surface angles and 3 central angles. There are also spherical polygons, in which a closed geometric object on the surface of a sphere is formed by arcs of great circles.
What is population dynamics?
One major area of interest in mathematical biology is population dynamics. A population is the number of individuals of a particular species in a certain area. Population dynamics deals with the study of short and long-term changes in certain biological variables in one or several populations. Population dynamic studies have actually been around for centuries. For example, weight or age comparisons of human or other animal populations, or even how such populations grow and shrink over time, have long been areas of study. With regard to human populations, the 2 simplest kinds of input in a population study are birth and immigration rates. And the 2 basic outputs are death and emigration rates. If the inputs are greater than the outputs, the population will grow. If the outputs are greater than the inputs, the population will shrink.
How do you expand logarithms?
Like an algebraic expression, it is possible to expand logarithms, which is a way of picking apart an expression. The following lists 2 examples of expanding a logarithmic expression. To expand log 2, 3x, equals log 2, 3, plus log 2, x, to expand log 2, 12/x, equals log 2, 12, log 2, x.
How are positions on Earth determined?
Positions on Earth are determined using two numbers that represent latitude and longitude. These numbers are actually two angles, measured in degrees. Degree, minutes of arc, and seconds of arc. On a globe of the Earth, latitude lines circle parallel to the equator and differ in length depending on their location. The longest line is at the equator, latitude 0 degrees, the shortest lines actually pinpoints are at the poles. 90 degrees north at the North Pole, 90 degrees or minus 90 degrees south at the South Pole. In the Northern Hemisphere, latitude degrees increase as you move north away from the equator. In the Southern Hemisphere, latitude degrees increase as you move south away from the equator. Longitude lines, or meridians, once called meridian lines and eventually shortened to meridians, are those that extend from pole to pole, slicing the Earth like segments of an orange, with each meridian crossing the equator. In the Western Hemisphere, longitude increases as you move west from Greenwich, England, 0 to 180 degrees. In the Eastern Hemisphere, longitude also increases as you move east from Greenwich, England, again, 0 to 180 degrees. All points on the same line of longitude experience true noon, and any other hour, at the same time. But note, longitude lines are not to be confused with time zones, most of which follow a more erratic demarcation. For more information on time zones, see below. For more information about latitude and longitude with regard to polar coordinates, see geometry and trigonometry.
How are the principles of ratio, proportion, and symmetry applied to architecture?
The definition of a ratio is a comparison by division of two quantities expressed as the same unit measurement. For example, a building that is 200 feet wide and 100 feet tall has a ratio of 2:1, 200:100, between its width and height. It is also seen as the fraction 1/2. Such a relationship was understood as far back as ancient Greece and Rome, when people used mathematics to give structure and aesthetics to buildings. This is especially important in architecture, in which building design is based on complex mathematical ratios. Proportion is an equation stating that two ratios are equal. Every proportion has four terms, with the first and fourth terms being the extremes. The second and third terms are called the means. In each proportion, the product of the means equals the product of the extremes. The Greeks and Romans often used proportions in their buildings and other structural designs. The Roman architect Vitruvius was also instrumental in praising the virtues of proportion and symmetry in architecture. For more about Vitruvius, see above. During the Renaissance, architects applied proportion and other mathematical formulas to produce aesthetically pleasing buildings, beauty that still holds true today. Although there are other types of symmetry, the most common is line symmetry, in which a line divides an object, line, or other structure into two equal halves. An example in nature would be the wings of a butterfly. If a line of symmetry is drawn, each point on one side of the line has a corresponding point on the opposite side of the line. If you connect these 2 points, the line is perpendicular to the line of symmetry. There is a more mathematical way of defining symmetry. 2 points are symmetric about a line if the line is the perpendicular bisector of the segment joining the 2 points. Symmetry was used by ancient, and modern architects to maintain visual and sometimes structural balance of a building or structure.